Up next, we have Duncan Laurie with open source firmware. Duncan works at Google on the Chrome OS.
Okay. All right. Thank you, and welcome. So I'm going to talk today about the firmware stuff that we've been working on with Chrome OS, and in particular, the stuff that we're trying to do to open things up that are normally sort of very closed in the systems that you buy. Real quick, I've been trying to do open firmware for quite a while. I got my first taste of this back at a startup called Cobalt Networks, where we actually did a custom firmware that we did embed a Linux kernel to take care of a lot of the device setup. And then I sort of segued into server stuff and platform management and did some open source tools in that area before coming to Google and doing more server stuff. And today I am the technical lead for firmware on Chrome OS. So first off, what is Chrome OS? I know most people already know this, but I'll go over this very briefly. It is an open source project based on Gen 2 Linux. It really follows the same model that Chrome versus Chromium does. So there is a Chromium OS and a Chrome OS. And the Chrome OS version that is the Google branded version includes some third-party modules that are not open. In particular, things like there may be some video codecs left, even though we're finally getting rid of those. The Netflix plugin and some other PDF plugin, maybe, something like that. Chrome OS is targeted to very specific devices. It really isn't meant to be a general purpose solution. And a lot of the reason is that it's really hard to deliver a very polished experience for a user if you don't have control of the hardware, and in particular, the firmware that's on the system. And so we limit it to, we limit the Chrome OS version to the actual devices that we build and ship. That said, it is an open source project, and people have started making distributions of Chromium OS that they're making available for people to play with. Often it's easy to build and run in a virtual machine. We do a lot of our testing with virtual machines, and so you can pretty easily check out and build Chrome OS for a virtual machine. And the other thing about Chrome OS is that security is one of the sort of the founding principles of the project, and this security extends all the way down into the firmware, and in fact into the hardware. We sort of force the device manufacturers to do some things that they may not otherwise be prepared to do, including a read-only firmware and a TPM present in the device. And we use the TPM not for measurement, but mostly to store for its non-volatile storage to be able to keep version numbers for rollback protection. And just, I think the other day, Google announced that they're sort of putting their money where our code is, and Chrome OS is the focus of this year's Ponium project, happening in CanSec West, I believe, in Vancouver, in a little over a month. That should be interesting because the actual target is the device that I have here with me, which is our first device that actually shipped with our open firmware stack that I'm going to talk about today. So why do we invest in firmware? Why do we think this is important? We very easily could have just licensed an EFI firmware base from one of the independent BIOS vendors out there and shipped with that. And in fact, that is what we did for the first 2 generations of the product. And there wasn't a lot of downside to that, except at the end of the day, the firmware that we produced, we had no hope of being able to open source any of it. Even our verified boot implementation that we did, the integration of that into the vendor's EFI code base was then sort of kept proprietary. And so we thought, why not be a little disruptive and see what we can do to really open things up and see how far we can push things. And this goes beyond just the host firmware. I'm going to talk about embedded controllers as well, because we think those are also very important. So a couple of reasons why also to invest in firmware is that it really helps to know about the platform that you're building. If you want to deliver a very polished end user experience, you've got to know about the hardware you're building on. And firmware is really hard. It's not an easy problem. These systems are getting more and more complicated, and it's getting really hard to put together sort of a hobbyist user to put together a firmware for a modern system, especially a modern Intel system or one of the newer ARM processors. And when you're working on firmware, bugs are going to be found. These are going to be found in every layer of the stack, both software and even in the hardware. There's going to be board issues. You're going to run into chipset problems, problems with lots of devices that are trying to be plugged in. And in particular, for someone working on firmware, firmware is always blamed first. Every bug that seems to be filed when we work on a project is, initially filed in the firmware category, and it's up to me or one of my developers to sort of figure out what the actual bug is and sort of point the finger somewhere else. And that means that firmware developers are generally really good at debug as well, because they really need to know about the hardware and all of the various, bus protocols, low-level stuff, assembly language, all that stuff to be able to understand the firmware, and that actually makes them really good at understanding where bugs come from. And as was mentioned in Bunny's talk this morning, time is money. If you don't ship a product on time, then you're going to miss either Christmas sales or various things. And so if you're not involved in the firmware for the creation of the hardware that you're working on, you kind of are at someone else's mercy when it comes down to actually meeting those schedules. And control of the platform is also important. And this starts with being able to deliver a consistent behavior across different architectures. And so both our x86-based systems and our ARM-based systems deliver pretty much the exact same user experience from a firmware perspective, and that's largely because the firmware executes and gets out of the way as fast as possible. But it allows us to then be consistent and not sort of present a different interface for different platforms. It allows you also to maximize the power and the performance, and this kind of comes back to knowing about the hardware that you're working on to be able to get the most out of it. And for firmware in particular, the goal is to boot as fast as possible. With our first generation EFI-based systems, we, I think, got down to about 1.5 seconds for firmware time. With this particular one here, we got to just over 1/2 second, to being totally out of the firmware and into the kernel. And then controlling the firmware allows you to do some interesting things at that firmware OS boundary where you've got interfaces that need to talk to hardware and do interesting things. I'm going to talk some about the components that make up our firmware stack, and which ones are open, which ones are not yet open, and which ones have no chance of really ever being open. I'm going to focus on the x86, the Intel side for the moment, because that's the one that that I've got in front of me, and that's the one that I worked on the most over the past couple of years. So I'm going to go through each of these components here in a little bit more detail. So the foundation of the firmware is Coreboot. Coreboot is a project that started in 1999 by a guy named Ron Minnick. He was at LANL, which is a government lab in the US, and his goal was to boot cluster nodes really fast. And he got really tired of a legacy BIOS that if you had a system built and there was no keyboard plugged in, it would boot up and say, press F1 to continue, which is really hard if there's no monitor to see that message, and even harder if there's no keyboard to press F1 on. He loves to tell this story. So in 2008, the project was taken over by someone named Stefan Reinauer, and it was renamed to Coreboot. And part of this was because that the Linux BIOS project didn't actually use or include a Linux kernel, and so it wasn't really aptly named. Coreboot was sort of a more generic name that allows it to mean more than one thing. We have managed to hire both Stefan and Ron at Google on my team, and so they both work with me now, which actually made picking Coreboot a pretty easy choice for us at the time. Coreboot's made up of mostly C code. There's a little bit of assembly glue code that sort of starts everything up, and then there's a bunch of ACPI code. And I'll talk more about that fun in a minute. The high-level organization of Coreboot is actually pretty similar to EFI. These days, there's a fairly straightforward set of things you need to do to get a system up, and so it's not that surprising that they all sort of have the same stages, they just name them different things. And in particular, Coreboot does not include a bootloader by itself. It really has a concept of a payload that allows you to be flexible with what you do when you try and actually boot a system. So real briefly here, the stages of Coreboot, it starts up with this boot block mode, and the goal of the boot block is to set up the CPU's cache as a stack or RAM so that you can then be able to run some C code before you actually have full memory up and do any preparatory stuff to get flash access. The boot block in Coreboot is partly assembly code, but it's also partly a very limited version of C that's compiled with a compiler called ROMCC that attempts to use the registers in the CPU instead of a stack so that you can do a very limited C code because no one really likes assembly. And from there, once you've got this a little bit of stuff set up, you can jump into the ROM stage. In EFI, this would be the equivalent of PEI. And this is in charge of getting memory up. This is again, mostly C code. It is still a very slightly limited version of C code because it is executing in place out of the SPI flash. And so you have to worry about things with global variables and things like that. At the end of ROM stage, you're supposed to have memory up, and then you can load and decompress a RAM stage from the flash and jump into that, where you have a more full-featured environment. This would be equivalent to the Dixie stage in EFI. RAM stage is responsible for sort of enumerating devices, assigning them resources, creating all these ACPI tables to make the OS happy, installing a system management mode handler, and all sorts of other interesting things. And then, as I mentioned, there's a payload at the end of all that that allows you to actually boot something interesting. The next step in our stack, our payload that we use in our current generation, is U-boot. And U-boot is an interesting choice for x86. It's more commonly known as the ARM bootloader that is used in a lot of consumer electronics. Although these days with Android using a fast boot specification and EFI making its headway into ARM, U-boot may actually be shrinking a little bit. And the reason we chose U-boot for x86 was that we'd already done the work to integrate our verified boot into U-boot, and so it actually meant that we were able to take advantage of all that work without having to redo it. We are looking at whether or not this is the right solution going forward. U-boot is a pretty heavy project for what we do, for just trying to boot. But we did upstream all of our work, and you can actually find that in the upstream U-boot repository now. I should point out that I have a link here to the bottom of the slides, and I have a lot of links in my slides because I want people to be able to learn more about the stuff that we've done and sort of follow along if they're interested. So the first closed part I'm going to talk about is what you need to do to actually get memory up in an Intel system. Intel, when you license from them as a BIOS vendor, you get a big chunk of code, probably about 6 or 7 different blobs of code that come from them that are all these different reference code. This will initialize early CPU stuff, some chipset stuff, but the most important piece is the one that actually trains and initializes memory. So what we did, this code normally comes as EFI modules that plug pretty easily into an EFI BIOS. Because we don't have that EFI structure, we actually wrote a very simple PEI wrapper that allows us to produce a standalone binary out of the code that they give us. And so we can then take this binary and sort of put it separate into the flash, executed it at the in ROM stage, and when it's done, you've got memory. Kind of black magic still. For the Sandy Bridge and Ivy Bridge generation, we were able to actually release this binary blob sort of as a standalone binary and put it up on a corporate repository. Things have changed a little bit with Haswell. The distribution terms aren't really going to allow us to do that directly. However, we have been working with Intel to try and come up with a way for them to be the one that provide this binary. And so this is a project at Intel called the Firmware Support Package. And they actually have some details up on their webpage now. They've given a talk. Actually, I think there was a talk last week by the guy that it's working on, it's Jiming's son at Intel. So they're making some strides to sort of be the ones that own this binary. The next piece that is completely closed and has no chance of being open is the management engine. This is the thing that a lot of people don't know about it. It is a microcontroller that lives in the South Bridge in Intel chipsets. This microcontroller runs a blob of firmware that Intel provides you. That firmware is either 1.5 megabytes or 5 megabytes, so it's actually really huge. It's required in every Intel system these days. You used to be able to get away with it sort of by either nulling out that region and it would sort of sit there and do nothing. But the management engine does do a lot of features, and in particular the one that they like for mobile devices is that it can be the clock generator. And so that way they can remove another chip from the board and replace it with something that's already there. From my perspective, it really reduces our control over the platform, and it makes it really hard to debug the system. You actually don't come out of reset anymore if the management engine is not happy, which means that you kind of wonder why your system's doing nothing, and it's not your code, it's that you haven't configured this code correctly. You have to configure the management engine binary for every board that you put it on, and there are subtle changes that need to be made to it, and you can only do that with a tool from Intel that runs in Windows. So I don't have too many nice things to say about the management engine, so I'm just going to move on. Video is another big one for us. Normally we actually don't need to display or want to display any video in firmware because the goal is to boot as fast as possible. Thanks to the work by the Intel graphics team, the i915 driver in the kernel is actually able to bring up and initialize the graphics on its own as long as you set up certain things properly in the registers beforehand. Usually enough to describe the magic timings that are needed to make the panel actually come up. However, we do need graphics in the firmware for recovery mode and developer mode to be able to display stuff to the user. And so that means currently we actually do include the binary option ROM that's provided to bring up graphics. But we've been looking at what we could do to extract the kernel driver and extract the initialization parts from the kernel driver and actually provide them as open source in our firmware. We haven't shipped a product with this yet, but we have been playing with the code and playing with the concept. And we're using a semantic patch language, which basically does sort of matches and transformations on C code to extract the stuff you're interested in and stub out all the dependencies without having to bring the entire piece of code in. So yeah, we haven't actually shipped with this yet, but it's still on our list. Now this one is the one that's actually closest to my heart is the embedded controller. This is another microcontroller that lives in pretty much every notebook device out there. This is a microcontroller that there are several different vendors that make them. A device manufacturer will usually pick one of these chips, they'll license a firmware base, they'll customize it, and then they'll actually customize it further for every device that they build. The embedded controller runs even when your system is completely powered off. It's there to do battery charging and to do all sorts of these key platform tasks that are hard to do in the host when you don't actually have the host up and running yet. I've listed a bunch of them there. I'm not going to go through them. The big one, though, is actually power sequencing. On an Intel chipset in particular, the power sequencing is done by the embedded controller. So you're actually never going to get the system up and running if your embedded controller doesn't sequence the power properly. For x86 side, the embedded controller usually lives on the LPC bus today. There's some work underway to sort of move this to the SPI bus, which will be sort of good for some things, but sort of bad for complexity because LPC is really easy from the host side. There's usually at least two interfaces to the embedded controller. One's going to be a firmware interface that uses a custom protocol and usually system management interrupts. And then the other one is a OS interface that's usually done through ACPI. I'll cover more about the ACPI interface in a minute in gory details. On the ARM side, there isn't a lot of common interfaces, possibly because there's not a lot of ARM notebooks on the market. We're sort of having to figure out our own interfaces as we go along. These are usually connected over I2C or, as I said, moving to the SPI bus eventually. On ARM, you can often share the same interface because your firmware isn't resident after you've booted the kernel, which actually can make some things easy. So we set out and initially tried to remove embedded controllers from the system. We did a lot of work to try and build systems that didn't include an embedded controller at all. And we've kind of, for now, given up on that approach and instead decided to write our own embedded controller and make it open. As I mentioned before, all these embedded controllers are very closed. The hardware makers will license a code base, they'll customize it. They think they're providing a lot of value add in their embedded controller, but they also really aren't worried about security at all. And so this is actually a really big vector of attack. The embedded controller is your keyboard, and for older versions, it's also the trackpad. That's moving to I2C interfaces, though. But because it's your keyboard, it could do key logging and all sorts of really nasty things with just a very, little bit of change to the firmware. Right now, I think there sort of aren't a lot of attacks in this area, mostly because it's very obscure, and you really need to know about the device in order to be able to write firmware for it. Yep.
How would an attacker get at a microcontroller?
So you can generally update the firmware on these microcontrollers, so they will sometimes release firmware update packages, and they're generally, on the x86 side, it's an LPC bus interface to then update the firmware on it. And it's more of an obscure interface than any sort of secure interface or anything like that. The Samsung ARM Chromebook that we shipped a few months ago is our first device that actually uses our embedded controller. And this is based on an STMicro Cortex M4. So it's an ARM Chromebook with another ARM microcontroller in there. And if you look in the code base that I've linked above, you'll actually see support for other chips that are interesting that may resemble something you'll find in your recent Apple MacBook. In our case, we decided that update was also really important, and so it's actually part of the host firmware that we've specified, so it's part of our verified boot. So if the embedded controller does need an update, we release an update to the host firmware, and it takes care of updating the embedded controller. Okay, now I'm going to talk some about the features that are in the Chrome OS firmware. Obviously, the first one is our verified boot. Now really this is actually very similar to UEFI Secure Boot at a high level. I think we probably set off around the same time that the UEFI forum did, trying to come up with a way to make boot more secure. We explicitly avoided the word secure boot because secure is kind of a loaded term, and instead verified boot, which describes what it actually does, which is verify every next stage of firmware that is loaded. On our systems, the root of trust is actually in read-only firmware. And that means that in order to completely replace the firmware on your device, you need to open it up and defeat the write protection. And we publish documents on the Chromio.org for all the devices that we ship on how to actually do that. But it does add a layer of inconvenience, which is kind of intentional. What's inconvenient for you is also inconvenient for a hacker. It's certainly not going to stop someone that has local physical access to your machine for more than long. Our goal is, 5 minutes of, not having sight of your machine. Any more than that, and you probably shouldn't trust it anymore. So with the read-only firmware that starts up, it verifies any signed read-write firmware that might be updated, and then that verifies a kernel from the disk. And we've published implementation here. There's also the implementation in U-boot that we've also pushed upstream. This has a kernel component to it as well. Our root file system on Chrome OS is actually read-only as well. And when we create that read-only image, every block is hashed, and all those blocks are bundled up and stored in a tree. And then the hash of that first block in the tree is actually stored with the kernel itself and is signed, so that when the firmware signs it, it actually knows that the block hash it's going to pass to the kernel is something that it's actually verified. And so when the kernel comes up, every block that is read is hashed and checked against the tree, and you can structure that tree so that you actually walk down the tree as you're booting, so you don't have to waste a lot of time trying to find the hash that you're looking for. Once the block has been read and hashed, it's stored in the page cache. You don't have to do it again until you eventually run out of memory. This work was pushed upstream as well with the help of Red Hat. This is upstream in the DM Verity module that you can go look at for details on how it works. There's actually also documentation on the Chromium website that I linked before that is more focused on the kernel side than it is the firmware side. Specific to Chrome OS devices is that there needs to be some sort of way for a user to recover their system, either if it's been damaged for some reason or if a hacker has managed to get into there. And so there is a set of firmware that's entirely read-only that is used to only boot a signed USB image. Recovery mode will never attempt to boot from your local disk in case it's been compromised. And you can enter this recovery mode either if the system detects a problem or if the user manages to assert physical presence with either a switch or a button or using a special magic keystroke, assuming you have an EC that you trust. So on the Samsung ARM Chromebook that's out there, if you hold down Escape plus the refresh button and hit the power button, that actually triggers a special circuit, the Solego chip that we've put on the board, that ensures that the embedded controller and the host are both reset and that the embedded controller comes up in its read-only firmware, and then you can be sure that what you're getting is actually the user requesting recovery mode, not some sort of malicious software. Developer mode is also a big part of Chrome OS, and this is the jailbreak mode that's built into every device. And so Chrome OS is very locked down by default, but we really don't want to lock people out of doing interesting things with the hardware that they own. In the first generation devices, and including this one, there's actually a little switch in the key lock in this device that you can flip that will put the system in developer mode. On the newer ones, you actually get there by going into recovery mode and hitting, I think it's Control-D, and then it'll ask if you want to enter developer mode. When you do enter developer mode, you get a root shell in Chrome OS, and that allows you to start playing with the system. And then you can also enable booting of self-signed images, so you can sign your own images and put them on the disk or boot them off of USB. And developer mode does include a sort of scary boot splash screen that shows up on boot. This is sort of meant so that you know that your system is not necessarily in the fully verified user mode. Event logging. So this one is also really important to me. As I mentioned before, firmware is usually blamed for all the bugs that come in, and so it's really important that I am able to quickly point the finger somewhere else, if possible. And so we started using this event logging method in our servers at Google a long time ago, and it's been extremely valuable sort of as a way to figure out what the system has been doing before it got into this state that is now some unhappy state. And it's based on the SMBIOS system event log, although it uses a layer of OEM events on top of that to actually do something more interesting. And there is a kernel interface to this as well. So this is a driver that we wrote that's been pushed upstream. And this interface uses system management interrupts to actually tell the firmware to write out a kernel event into its log. And this way you can actually get sort of the reason that the kernel went down, as well as the reason that the firmware think the system went down. And then there's userland tools that can find and parse this log. So here's a quick example of an event log from a system I grabbed a couple of weeks ago. And you know, by default, the log just looks like it's full of all these events. But what it can tell us about the system is that, you know, it powered on because the lid was open at some point. The EC got an event saying lid open. And then the system went to sleep about an hour later. And then many hours later, it was woken from suspend due to a GPIO event. In this particular system, that GPIO 11 actually is the trackpad wake event. And then as soon as it woke up, it got an oops and a panic, and it rebooted. And so this, by itself, this doesn't actually tell me there's a kernel problem, because there could have been some other reason that the kernel panicked. But it does mean that the next step is to go and figure out where that kernel panic is and sort of understand what happened there. Memory console. So serial, when you're working on firmware, serial is really important, but it's actually really hard to come by, especially on a mobile device. You're never going to find a DB9 header on a laptop, unfortunately. And so we actually store all of the console output while we're booting into a memory buffer, and then we have a kernel driver that exports that in sysfs. Obviously, this isn't useful if you're not able to actually boot to an operating system to see this, but it is useful for systems when someone, you know, brings me a laptop at work and says, what's going on? This thing came up in a weird state. I can go and look and see the firmware log and see if anything looks out of the ordinary. This isn't exactly a firmware feature. I'm going to briefly touch on ACPI, mostly because I'm going to show some code from it. ACPI stands for Advanced Configuration and Power Interface. It's really a way of describing the hardware that you're going to boot and presenting it to the OS in sort of an OS-agnostic form. But the other piece that comes with ACPI is that there is firmware code that is then executed in OS context. And so from our perspective, this means that the firmware is providing code for the OS to execute, and you really want to trust where that code comes from. Although it's probably better to be executed in OS context than behind the scenes in system management mode. The source language for ACPI is pretty ugly. I believe Linus once described it as a design disaster, and I really can't argue with him. Every variable and method is exactly 4 characters. This makes for easy parsing of the bytecode. And if you don't make your variable 4 characters, it will pad it with underscores in the actual resulting bytecode. But it also means that it becomes really hard to follow the source, because everything is these, you know, magic 4-character keywords. ACPI uses the system control interrupt to interrupt the OS and let it know that it needs to handle some sort of event. It also uses SCIs to sort of drive the communication protocol and makes a kernel so it doesn't have to pull on these I/O ports. Okay, I'm going to talk about the boot process, both for an Intel system and the ARM system. So I mentioned earlier the stages of core boot, so this one looks pretty familiar. We start up in ROM stage. I'm kind of skipping boot block here. We run this vendor binary that's closed that gets us memory. Then we go into RAM stage. We load U-boot, and then we load potentially a read-write firmware that might contain any fixes or updates. Excuse me. And then from there, it loads a kernel. I mentioned A and B here because we have 2 copies of firmware. You may update your firmware B, tell us to try and boot that firmware, and then you may do the same with the kernel. These don't actually have to be tied together like I showed in this image. Firmware A could load kernel B and whatnot based on priorities that are set in the GPT partition table. So looking at the ARM side, this is also a mix of closed and open components. So this is based on the Exynos 5240, I believe, which is Samsung's A15 chip. So there's actually 2 binary components in the very early part of the boot process here. The IROM is sort of something that's, I'll get to these in detail in a sec. I just want to mostly show the picture on this page, where you can see that we start in these vendor binaries. Eventually we get to a version of U-boot that then loads a more complicated version of U-boot that then loads into the verified boot and does the same steps as the x86 side. So the IROM is this on-chip ROM. It comes from the vendor with this code already loaded. The goal of the IROM is basically to verify and load BL1. BL1, we believe, stands for bootloader 1. It's never really been defined. It's sort of a very early pre-boot firmware. This is also provided by Samsung, and it's a signed firmware image. It does very early chip initialization, and its goal is to verify and load the BL2. BL2 is actually code that we own, or we produce. And BL2 is actually based off of U-boot's secondary program loader, which is just a very stripped down version of U-boot. And its goal is to then set up memory and load a more full version of U-boot into memory. And then once you get into U-boot, you can start doing the same steps as we see on the Intel side, where we've got actually a shared code base that does the verified boot stuff and boots the kernel. Okay, so I'm going to go into an example that actually tries to tie all of these various firmware components together and show why we think it's important that all of these different steps be open. So the example I'm going to talk about is the laptop lid policy. So when you shut your laptop lid, your system goes into suspend, but how does it actually make its way into that state? A very basic laptop lid policy here for Chrome OS is that if the users manage to log in, we go into suspend, otherwise we turn the system off. Pretty straightforward. Does not take into account more advanced cases like you've got an external monitor and some keyboard plugged in and you want to have your laptop tucked out of the way. That can be left for a higher level, thankfully, and I don't have to worry about it in firmware. But I do need to be sure that the behavior in firmware and the OS is consistent. For firmware, this means the user is never going to be logged in firmware. So basically, if you get a lid event in the firmware, you just turn the system off. But where does that lid state come from? And how do you get notified that the lid state has changed? These are actually connected to the embedded controller. So a laptop lid is a pretty simple Hall effect sensor. The voltage output changes based on a magnet that's put next to or removed away from the sensor itself. And so that voltage is connected to a GPIO pin on the embedded controller. And so when the state changes, the embedded controller can get an interrupt and it can decide how to service it. Describing the lid to the OS is done in ACPI here with this code that I've shown. You've got a magic identifier so the kernel knows that this is a lid device, and you've got a special also predefined magic method called _lid that will return a value of 0 or 1 that indicates whether the lid is open or closed. In this case, it's actually going to go and query the embedded controller to find out the current state of the lid switch that the embedded controller knows about. So to describe the embedded controller in ACPI, you have to do a little bit more work. This is a very stripped down, simplified version of an embedded controller description. You can find more detailed ones in the Corbett repository for the systems that we've released. Let's see, the stuff to mention that's important on here. There's a memory map that the embedded controller exports that's really a way to provide a bunch of state that can then be easily read throughout the rest of ACPI. Lid switch is one of these examples. You'll find the battery information is also in this table and is then molded and presented through the battery device that ACPI defines. The interface to actually talking to the embedded controller is defined there as well, using ports 62 and 66. And then I've defined a method for a lid close event. And this is, again, the _Q is a magic nomenclature in ACPI, and in this case, _Q5E means that if the embedded controller says, I got event 5E, you go and run this method and it'll actually do the next steps. In this case, it actually just does a notify on that lid device that we presented earlier, and that notify will then tell the kernel it needs to execute that magic _lid method and figure out what the state of the lid is. So pretty straightforward on the embedded controller side. Someone closes the lid, a GPIO interrupt happens, you set your lid switch, your current lid state to 0, and then you generate a lid close event. What kind of event you generate depends on whether you have entered ACPI mode or not. And if you have an ACPI aware OS, when it's booting up, it will actually trigger an interrupt into the firmware that will then also be passed down to the embedded controller that says, okay, I'm going into ACPI mode. From now on, stop sending me system management mode events and start sending me system control events so that I can handle them in the OS instead of in the firmware. But first, on the firmware side, you will take a system management interrupt. And this is a special non-maskable interrupt. It is the highest priority interrupt in the system, just below, I believe, reset and stop clock. And system management interrupts are used to enter system management mode, which is a magic mode in the Intel, or in the x86 processor world. And this can be triggered for a number of different reasons here. I/O and memory transactions are a pretty scary one. You can actually trap on any I/O or memory transaction and jump into system management mode. This has been used for really ugly workarounds for broken hardware. But in doing so, you actually lose control of the system, and you actually start losing system time, and the kernel gets really confused and unhappy. System management mode is really terrible in servers, especially if they need to keep their clocks in sync for things like locking. In our case, it's an external pin. When you take a system management interrupt, your CPU state gets stored in this special region of memory. Your instruction pointers change to the start of your handler. all the CPUs will enter system management mode. There isn't one CPU at a time. They may not enter at the same time, but they will all eventually get there. And there's a special instruction called RSM that will resume back to normal behavior. So if we want to look at this from a visual perspective, we have some CPUs that are running along. They get a trigger that says into system management mode. They jump into the assembly stub, the SMM handler start. This is actually a link if you want to go see where this is in Coreboot. There's a spin lock here. In Coreboot, we really only let one CPU run the full system management mode handler. It makes things easier than having to wait for all the CPUs to check in because they may not enter at the same time. So one of these CPUs will fall through the spin lock. It'll execute the full handler that will eventually go and read the event code from the embedded controller to see you got a lid close event. If you did not get a lid close event, they'll just go back and resume. Or if the lid state was actually still open, all the CPUs will resume and you'll go back to where you were before. If the lid is closed, the system will shut down. And so we've got assembly code executed by all of these CPUs and the C code executed by just one of the CPUs. Now from the OS side, things are slightly more complicated because you have to deal with ACPI. So in this case, we start with a lid close event. The EC will generate an SCI to the host. This is a notification SCI, which is a little different from a completion SCI. The host will say OK. The embedded controller driver in the kernel will go and read the event code, will go and attempt to read the event code from the embedded controller. The embedded controller will say, OK, the event that I've got for you is this magic 5E. This actually corresponds to the lid close event on this laptop in front of me. It'll return back this 5E code. And then the I believe this is still the EC driver in the kernel, will go and attempt to execute and find this special defined handler for the 5E event. That will then generate a notify to the lid device, which will then go and execute its lid method, which will then go and attempt to talk to the EC again to figure out the current state of the lid switch. And so it'll ask the EC will say the lid is closed, returns a 0. And then the lid close event is propagated up into the user space via proc ACPI event or some other event method. And then you have a higher level policy that sort of decides what to do. In our case, we're going to suspend or shut down depending on whether the user has logged in or not. And so here's the whole thing in a gory detail. All of these descriptions on the right and left here are actually links to the actual code where this takes place, which is, to me, a very important thing, that it means that every step of this is open, if possible. Unfortunately, the embedded controller in this device is not open yet, so the EC stuff that I'm linking on the side is actually for an implementation that isn't released yet, or that isn't in a product yet. And I kind of lied a little bit. The event query is actually a little more complicated, as usual. So I'm not going to go through this in too much detail because I'm running out of time. But it's an IO port-based communication back and forth between the embedded controller to actually get that code back from it. And as you can see, there's different kinds of SCIs that will come in. You'll either have an event SCI or you'll have one that's mostly meant to just prompt the kernel along in its communication method. And that's it. Any questions?
When you actually optimized down from 2 seconds to half a second, did you actually use any explicit parallelism, or did you just simply not do things?
It's largely not doing things. The biggest thing that we found was even to get to the 1.5 second boot time that we did, we had basically morphed EFI so much that it really didn't look a lot like EFI anymore. Just by switching to a much simpler code base that we have here with Coreboot, we actually saved most of our time just by being smaller and more efficient. And not doing things, obviously. Don't run a video option ROM. Don't initialize devices if you don't have to. You know, you're not going to boot off USB in a normal case, so we don't have to worry about bringing up USB and those kinds of things.
Sorry, I may have missed something early on. Are you using ACPI in all the Chromebooks or just the x86 ones?
At the moment, just the x86 ones. It is an interesting target for ARM as well because it does allow the firmware to describe things in a sort of a way that the OS, that you don't have to worry about the details in the OS of what the hardware looks like. You just sort of respond to the tables.
Right. That's not the only method.
No, definitely not. The device tree, U-Boot is starting to move to a device tree method that's actually just as powerful as ACPI, except for it doesn't worry about the firmware code that the OS has to execute.
Yeah, doesn't it? Right. So, I mean,
we currently use device tree on the ARM Chromebook that's out there. And so, yeah, you can find all that in U-Boot and in the kernel.
Okay.
Okay, you said your secure boot implementation wasn't actually the UEFI one. You have your own proprietary one, well, your own personal one. Have you got any plans to actually move over to being UEFI compliant with the
Not at
standard
the
one?
moment. It's certainly something that is, one of those things we have to keep evaluating as we go. When we set out to do this, there was no UEFI secure boot, and so we sort of worked on our own implementation. It's one of those things that I think eventually we'll be forced to reevaluate whether using a UEFI secure boot is just the right option. I think as sort of the initial bugs and quirks are worked out, it's going to look like more and more of an attractive target. But we sort of like what we have today, and our security people are pretty happy with it. So.
Okay, looks like there's no more questions.
Okay.
Thank you for the talk.
All right.
And here's a little gift from Linux Australia and the conference organisers.
Thank you.